Hello everyone, my name is Niu Tianxu. Today I will introduce the topic size distribution of golden nanoparticles in solution measured by single particle mass photometry. Golden nanoparticles have attracted widespread attention due to their physical and chemical stability and safe for biological use, making them important for application in biosensor. However, the utility and applicability of golden nanoparticles depend on their size. Currently, commonly used methods for measuring size indicate dynamic, dynamic light scattering (DLS) and transmission electron microscopy (TEM). However, DLS has limitations when measuring particles smaller than 20 nanometers, as its signal strength is proportional to the 6th power of the particle diameter. On the other hand, TEM has a low throughput. Therefore, we need a faster, lower cost, and more accuracy method for measuring particle size distribution in solution, especially the particle with diameter less than 20 nanometer. Interference scattering microscope (ISCAT) can meet this then. The ISCAT technique utilizes a laser beam that is emitted in parallel to illuminate the sample. When the light passes through the glass interface, a parallel reflected light is generated. The scattered light produced by the illuminated particle is when focused on a camera and interference with the reflected light, thereby enhance the signal. Here, we introduce the formula related to ISCAT signal. Formula 1 describes the intensity detected by the camera. I detect is intensity. E is incident electric field. R is for reflection. S is for scattering. Delta phi is the phase difference between the reflected and scattered light. Formula 2 assumes that R is bigger than S, thereby neglecting to S squared and set delta phi equal to pi. This background normalization when defining the ISCAT contrast as following. Using ISCAT intensity over background intensity can get contrast of ISCAT. The magnitude of scattering term S is linearly related to the volume of particles. It means that the larger the particle volume, the stronger the scattering intensity. In Formula 4, the locus C term is a constant, which includes the reflection constant and dielectric constant. SNR is proportional to the root of n, where n represents photon electron. This indicates that continuously increasing the laser intensity will continuously raise the SNR. At this point, the camera's forward capacity will limit the upper bound of the SNR. This is a diagram of ISCAT microscope used in the experiment. 520 nanometer laser is used to illuminate the gold nanoparticles, producing reflected and scattered light, which is captured by camera 1. 462 nanometers laser is paired with camera 2 to achieve autofocus through total internal reflection, and a partial reflector (PR) selectively filters some of the reflected light to reduce background signals. During imaging, camera 1 captured a speed of 500 fps with an exposure time of 2 milliseconds. We prepared the ice gas sample using polydilysing coated cover slip with concentrations of 5 nanometer, 10 nanometer, and 15 nanometer golden nanoparticles at 1 nanomolar, 0.5 nanomolar, and 0.9 nanomolar, respectively, each dropping 400 microliter onto the glass. Polydilysing is positively charged, and negatively charged golden nanoparticles is adsorbed to its surface through electricity attraction when they land. After measuring the three different sizes of the golden nanoparticle using TEM, we obtained the corresponding size distribution graph. On average, the measured range for 15 nanometer golden nanoparticles was 15.15 to 15.05 nanometer, indicating very high accuracy. However, for 5 and 10 nanometer golden nanoparticles, the measured average size was 5.73 to 5.68 nanometer and 9.32 to 9.24 nanometer, representatively, showing a noticeable offset. These measurements still fall within the manufacturer's state 10% error range, demonstrating the reliability and consistency of the measurement method. In this experiment, it is important to currently identify and reduce background noise. To do this, we use changes in the image over time to remove static background, which help us see small short-term signal more clearly. First, we create a low-pass image by applying Gaussian blur to the original image. When we divided the original image by the low-pass image to get the high-pass image. This process makes unclear detail easier to see. Next, we take the average of two sets of image sequence called x1 and x2. We calculate x2 divided by x1 to get the final XR image on the right. In the XR image, we can see that the particle signal is strongest at frame 4, showing that the particle touched the glass surface at that time. The advantage of this method is that even the particles doesn't stay on the surface but move up and down, we can still see a dark signal, each showing the particle touch the surface n times. We also make sure that only one particle lands in the window at one time to avoid overlapping signals. We choose diffusion instead of separation to remove the background. Separation could cause very small value to turn into zero, making some details disappear. Diffusion avoid this problem because it keeps the background close to one and shows more detail. Here we present the processing steps from raw data to the final radiometric image. A is raw image. B is the image processed by Gaussian blur. C is the high-pass filtered image obtained by dividing A by B. D is average of 50 frames before the landing. E is average of 50 frames when golden nanoparticles start landing. F is the radiometric image obtained by dividing E by D. In this processing, low-frequency structures are smoothed to an amplify of 1, which help improve image quality. Notably, the contrast range of the radiometric image is more sensitive than that of the average image, allow us to more effectively identify and analyze the landing event of nanoparticles. We showed the tracking of the signal 10 nanometer golden nanoparticle. Figure A highlights the position of the golden nanoparticle in a specific frame with a scale bar for reference. Figure B shows the contrast along the blue line with SNR of 7.35, showing the signal chirality. Figure C displays a two-dimensional Gaussian fit applied to the golden nanoparticle. The fit shows an amplitude of 0.982 plus or minus 0.001, and the position of and width parameter include a 95% confidence interval. Figure D shows how the Gaussian amplitude changes over time, reflecting the particle's behavior at its nearest the surface. From this figure, we can see that the particle in figure A reached its highest radiometric contrast at frame 6942. For the histograms of radiometric contrast for three different particles and their analyzed method. Figure A, B, and C shows the contrast histogram record after the landing of 5, 10, 15 particles in the experiment, showing the spread of landing event for different particle size. After performing a two-dimensional Gaussian fit, the results show that the fall width at half maxima is 316 plus or minus 6 nanometer, make it hard to directly determine the size of the particles from the images. However, the array diffraction rings around each particle become more noticeable as the particle size increases. The method used in the experiment involved observing the radiometric contrast of the particles and creating a regression line between the radiometric contrast and the known size of the particles. Figure F shows the relationships between the average size measured by TEM and the regression contrast. The connection between the average diameter determined by TEM and the average contrast measured by iSCAD for each solution proposes the regression model of C in Formula 4. Here, we compare the size distribution of golden nanoparticle determined from combined iSCAD experiment and TEM image. The distribution of 5, 10, 15 nanometer samples are shown respectively in green, yellow, and blue. Both methods give similar mean and median size for the 5, 10, and 15 nanometer golden nanoparticle sample, showing that iSCAD is the reliable technique for determining nanoparticle size. In addition, the gradient in the width of the diameter distribution between iSCAD and TEM further supports the linear fit between interference contrast and d-qubit in Figure F. Conferring iSCAD as a method for nanoparticle mass photometry. iSCAD has three advantages. First is high throughput. iSCAD can quickly measure nanoparticle size distribution, analyzing up to 4,000 particles per minute. And the second is minimal sample requirement. Only small volume and the low concentration of nanoparticle solvents are needed. And the third is background-free signal. The use of interference scattering produces a clear signal that is less affected by background noise compared to traditional methods. This experiment shows the measurement accuracies of iSCAD in the size distribution analysis. Thank you for your listening.